Okay. Thank you very much, Dr. Meng, for your introduction. Today, my report topic is about automatically learn scheduling heuristic by genetic programming. I will begin by introducing the job shop scheduling problem, followed by an overview of the classical genetic programming process. And next, I will present our advanced genetic programming methods, which focus on fundamental research. And all these methods are mainly tested on dynamic flexible job shop scheduling problem. And after that, I will transition from fundamental research to real-world applications, extending beyond the job shop scheduling to include genetic programming's application in workflow scheduling and inventory control. And finally, I will discuss future research direction. So first is about the background knowledge. Job shop scheduling is a classic combinatorial optimization problem where a set of jobs must be processed on a set of machines with the objective of optimizing resource allocation. And for job shop scheduling, each job consists of a fixed sequence of operations, and each operation can be processed at a specific machine. And for the main constraints, it includes first, an operation can only be processed after its preceding operations have been processed, and the processing of operation cannot be stopped until it is completed. And also each machine can process at most one operation at a time. While common objectives in existing studies include mixed span, flow time, and tardiness. Flow time is defined as the duration from a job's release time to its completion time. And here is an example of scheduling 3 jobs on 3 machines, and each job includes 3 operations. The right figure shows the schedule results. And flexible job shop scheduling is an extension of job shop scheduling. For flexible job shop scheduling, different from job shop scheduling, each operation can be processed on a set of machines, and the processing of an operation depends on the machine that processes it. Another type is dynamic job shop scheduling. So as the name implies, dynamic job shop scheduling needs to consider some dynamic events like random job arrivals, like machine breakdown, or like order cancellation. And this table summarizes different types of job shop scheduling problems, while our research mainly focuses on solving dynamic flexible job shop scheduling problems, since this problem is much closer to the real-world application. And for this problem, we need to consider 2 types of decision point, which are routine and sequencing. And also, the job information is unknown in advance. And existing methods for job shop scheduling can be categorized into 3 types, which are exact approach, meta-heuristic or heuristic approach, and hyper-heuristic approach. Well, for exact approach, like branch and bound dynamic programming, they are more suitable for solving small-scale and static problem, but cannot be used for solving very large-scale and dynamic problems. And for meta-heuristic methods like genetic algorithm and ACO or PSO, they can be used for solving some large-scale problem, but they are mainly used on some static case. For dynamic case, they might need a rescheduling process, so still not very efficient. And another type is the scheduling heuristic. Well, scheduling heuristic here we mean the manually designed scheduling heuristic. They can be used for solving a large number of job shop scheduling problems and can give the feedback in real time. But actually, this kind of methods needs some domain knowledge from experts to design different scheduling heuristics based on different scenarios. So we have another hyper-heuristic methods that try to evolve scheduling heuristics. which can perform better than the manually designed scheduling heuristics, which are like heuristic selection and heuristic generation. For heuristic selection, genetic algorithm hyper-heuristic is one type. Reinforcement learning can serve as both heuristic selection and heuristic generation. But currently, reinforcement learning is primarily mainly used for solving some small-scale drop-shot scheduling problems, and also its interpretability remains limited. Genetic programming has been extensively studied for dynamic flexible drop-shot scheduling, and it can offer better interpretability. So therefore, for our fundamental research, we mainly focus on improving genetic programming methods for the dynamic flexible drop-shot scheduling. And for dynamic flexible drop-shot scheduling, as I mentioned, two types of decisions should be made, which are routing and sequencing. So for the representation of genetic programming, we have two trees. The first tree represents the routing rule, and the other tree represents the sequencing rule. And the routing rule is to make machine assignments, and the sequencing rule is to use to select operations for an idle machine. And here I give a table. This table represent an example of normally used terminals and the functions to construct the routing rule and the sequencing rule. And the terminals should represent some scheduling states at decision point, like the number of operations in the machine's waiting queue, or the processing time of the operations by the machine. And the function side can include some normal functions like add or max or min. And here is the learning process of genetic programming. Here the low-level heuristics we represent the manually designed heuristics, or we represent the terminals like the processing time. And then we first initialize or generate a population size of scheduling heuristics. And then the learning process include individual evaluation, selection, and breeding. So this process repeat until the stopping condition is met, and we will finally output the best learned heuristics. And here is an example of the crossover process. As we have parent A and B, so we randomly select a crossover point and we sweep the subtree and the crossover point. We will get two offspring. And here is an example of mutation. Similarly, we need to randomly select a mutation point, and then we randomly generate a subtree to replace this mutation point. And finally, we will get a offspring. So after understanding the background knowledge, I will then describe the proposed specific algorithms, which can be categorized into 4 parts. So for part 1, I will introduce about novel parent selection mechanism. And for part 2, I will introduce the joint decision-making by integrated ensemble learning. And part 3, I will talk about collaborative heuristic generation and selection by genetic programming and reinforcement learning. And part 4, that's about multi-objective genetic programming. So first, that's about novel parent selection mechanism. Overall, we propose 3 parent selection methods. All of them are expected to improve population diversity and finally enhance scheduling performance. So the first one is the cluster selection. Well, this method is straightforward. We divided individuals in the population into different clusters or groups based on their behaviors. And then every time a pair of parents are required for the crossover, we will randomly select 2 different clusters and then select individuals based on tournament selection from each cluster. So in this case, we can make sure the selected parents are different from each other. So here, for cluster selection, the key is how to divide the individuals into different groups, and we need to find a way to measure the similarity between individuals. So the proposed similarity estimation methods is as this algorithm 1. Since for the DFJSS problem, we have a large number of decision points. So in these methods, we randomly select 14 decision points. And on these 14 decision points, at each decision point for each individual, we calculate the decision priority. The definition of decision priority can be seen here. For example, we consider 3 sequencing decision points and 3 routing decision points. And for each decision points, we consider 7 candidate machines or operations. And then our individuals will give or calculate the priority of candidate machines. And the number here represents the priority of these candidate machines or operations. And then the 1, 3, 4, 6, 5, 7, 2 represent the decision priority for this decision point. So after calculating the decision priority, we calculate the Pearson correlation between individuals on the decision point. And then we get the Pearson distance. So a smaller Pearson distance means that the individuals are more similar to each other. So so after we know how to measure the similarity between individuals, the cluster selection can be done. And the cluster selection actually choose individuals that perform different from each other as parents, promoting diversity. And the diverse partner selection further considers the cooperative ability between individuals to enhance collaboration. So to calculate the cooperative abilities between individuals, we aim to determine whether one individual can benefit the other at a certain stage of the scheduling process. So to do this, we divided a large dynamic flexible job shop scheduling problem into several sub-problems. So for each sub-problem, it captures the patterns of different scheduling stage by using the proposed multi-case fairness evaluation. So we can see from this example, if we only have 8 jobs for these DFJSS individuals and we want to divide them into 4 cases, then we based on their arrival order, then we can get each case. And for each case, we get a case fairness. And for the algorithm 3, we can see that the alpha value is a very important value that represents the actual influence of individual X2 to individual X1. So for the diverse partner selection method, first we select the X1, the first parent, by using the tournament selection. And then we keep selecting candidates by also use the tournament selection like the X2. And then we calculate the alpha value to check whether X2 can benefit X1. If X2 can benefit X1, then the X1 and the X2 are returned as a pair of parents for crossover. And also our methods adopting a strategy to further maintain the population diversity by adaptively adjust the crossover and mutation probability. It's like once we find it's really hard to find a X2 to benefit X1, then we think the population diversity is not very good. Then we will decrease crossover probability and also increase mutation probability. And here is a detailed example about how to select the candidate X2. For example, individual 1 is the X1, and then we calculate the real influence alpha value for individual 2 and individual 3. As we can see that for individual 3, the alpha value is bigger than 0 and also bigger than a negative value by the individual 2. So in this case, the individual 3 and individual 1 will be selected as a pair of parents for crossover. And we also propose using another selection method, which is the Lex case selection, where diverse partner selection can identify parent pairs where one can benefit the other. But these candidates are initially selected through selection based on their overall performance across the entire dynamic flexible job shop scheduling instance. But the next case selection in this case is intended to identify expert individuals who excel or good at a specific case or specific scheduling stage. So, unlike traditional selection methods that aggregate fitness across multiple test cases or from the whole scheduling instance, next case selection will consider each test case independently in a random order during selection. And the motivation of using this method is that some individuals may be very strong in a subset of test cases, while weak in others, but traditional methods might remove these methods and ignore their ability. But next case selection will retain them if they are the best in certain case, and finally might leading to innovation. And the algorithm 4 represents the code for the next case selection. And we propose to use the popular epsilon next case selection, that is to give some relaxation when removing individuals from the candidate pool. So the overall process can be summarized like this. Firstly, we get a candidate pool from the whole population, and then we random generate a case order. And then based on the case order, we remove per individuals based on each case fitness. And finally, we will return an expert as parent. And here is the results of comparing cluster selection, diverse panel selection, and less case selection with traditional genetic programming. So as we can see that overall, genetic programming with less case selection performs the best. And the second part is about the joint decision-making by ensemble. Here is the overall flow chart of the proposed genetic programming with ensemble learning. Well, ensemble learning is a machine learning technique that combines multiple models, and in job shop scheduling domain represent the scheduling heuristics to improve overall performance. So instead of relying on a single model, ensemble methods leverage the strengths of multiple models to reduce errors and increase scheduling power. So for an ensemble to be effective, its individual models should be diverse, meaning they should learn different aspects of the data. So actually, if all models in an ensemble make the same decisions, combining them provides no benefits. So that's the reason why we expect individuals in an ensemble perform different to each other. And also a diverse set of models will reduce overfitting to specific patterns in the training data. So this can lead into better performance. So as we can see from this flowchart, we also have the population initialization process. But differently, this process will not only initialize some individual of scheduling heuristics, but also initialize ensemble of scheduling heuristics. So first, we randomly generate some individuals, and then we do the individual evaluation by using the multi-case fitness evaluation. And then after the evaluation of these individuals, we do the ensemble construction and selection. So this process will select individuals to construct some ensembles. And then we also do the ensemble evaluation. And for the ensemble evaluation, we use the voting aggregation function and also use the multi-case fitness evaluation that I proposed in part 1. And because we maintain a population that includes both individuals and ensembles, so for our parent selection or crossover or mutation, we also allows both individuals and ensembles as parents, and also allows breeding between individual and individual, individual and ensemble, and ensemble and ensemble. So a key novelty of our approach is maintaining a population that includes both individuals and ensembles, while proposing a class of strategies that enable evolution between them. While existing methods typically construct ensembles only after training individual models. So our methods, by allowing both individuals and ensembles to evolve together, it enables mutual enhancement. And also, strong individuals contribute to better ensembles, while high-performing ensembles might get the selection and the refinement of individuals. And here is a more clear description of the population. We first random initialize some individuals from individual 1 to 3 and to n. And then after individual evaluation, we will use the proposed ensemble construction and selection strategy to generate ensemble. To generate some ensembles. And then for these ensembles, we also do the ensemble evaluation. So based on this population, our crossover allow individuals and individual as parent, and also individual and ensemble as parent, and also individual and also ensembles as parent. Same for the mutation. The individual can be the parent, the ensemble can also be the parent. Here is the introduction of the ensemble construction and the selection methods. We also use the lex case selection that I proposed in part 1 to do the selection, because the lex case selection, as I mentioned, can improve the diversity of the selected elements in an ensemble. After lex case selection, we also conduct a similarity checking again. That is to say, for example, the blue and the purple individuals in the current ensemble. The blue one is an expert for solving the case 2, and the purple one might be an expert for solving the case 1. Then if we have 2 other candidates, like this purple one and this green one, because we already have an expert like the purple one to solve the case 1. So in this case, we will finally select the green one to add it into the ensemble. And our results also show that our proposed methods perform significantly better than classical genetic programming and the state-of-the-art ensemble learning methods. And the third part is about collaborative heuristic generation and selection by genetic programming and reinforcement learning. Before talking about the proposed methods, we first conduct a systematically comparison between genetic programming and reinforcement learning. We select a recently published genetic programming method and a recently published reinforcement learning methods. All these methods are tested on the same DFJSS dataset. And as we can see that, the genetic programming methods perform significantly better than the handcraft or we say manually designed scheduling heuristic, and also perform better than reinforcement learning methods. And besides, we also analyze the interpretability of the policy learned by genetic programming and reinforcement learning. First, we compare the routing rule and the sequencing rule size. For the reinforcement learning methods, because the network structure is defined in advance, so we use number of nodes to represent the size of the reinforcement learning. So as we can see that, because we define the network in advance, so the rule size keeps the same for all different runs. But for MTGP, because it can not only optimize the parameters, but also optimize the tree structure. So for different runs, we might get a different size of routing rule and the sequencing rule size. For this comparison, we can say that MTGP provide a smaller rule size. But it's true that if we predefined a smaller network, reinforcement learning can provide a smaller rule size, but we need to make a trade-off between performance and rule size. And currently, even with a large network size, reinforcement learning cannot perform better than genetic programming. We also visualize the structure of the learned network by reinforcement learning, and also the tree structure rules by the genetic programming. As we can see that here for the reinforcement learning, there are a lot of hidden layers, and for each hidden layer, there are a number of nodes. here I just show 4 nodes, but actually we still have additional 12 nodes. And also between nodes, there are too many bits. So this structure actually is very complex. And it's harder to analyze why, based on some input states, the decision can be made by this complex network structure. But in contrast, genetic programming produce a tree structure representation and making the learner model more transparent and interpretable. Like this tree structure can be simplified to a function here, and then we can analyze this function, like we can know which part may be negative, and also based on the definition of terminals, maybe like this rule prefer a machine with a higher processing time or with a lower processing time. So compared to reinforcement learning methods, genetic programming actually can provide good interpretability. So based on this analysis, actually, we propose a new method to combine GP and reinforcement learning. So this combined method is try to leverage the advantage of GP to improve reinforcement learning. Where reinforcement learning actually also have some advantages, like reinforcement learning's reward function provides feedback at each decision point, so offer more detailed and continuous performance evaluation. While GP usually use the total instance to get awareness of this scheduling heuristic. So this method actually is very straightforward. We use genetic programming, and we also adopting the niching strategy to learn effective and also diverse scheduling heuristics. And then this learned diverse scheduling heuristics will replace the manually designed scheduling heuristics as actions for reinforcement learning. And our results verify the effectiveness of the proposed method compared to traditional reinforcement learning methods and many manually designed methods. And part 1, part 2, and part 3 are all about a single objective genetic programming. And for part 4, we will talk about the multi-objective genetic programming. Totally, we propose 2 methods, which is to combine genetic programming with MOEAD and also combine GP with SGA2. So first, we talk about the MOGPD methods. For these methods, all the processes are quite similar to MOEAD. Like we need to divide the problem into different sub-problems by assign weight and neighbors. And also we do fitness evaluation. And because different objectives might have different range, we do fitness normalization. And a novelty here is we propose an individual to sub-problems mapping strategy. The motivation to have this strategy is because GP search on heuristic space, and a smaller change on the heuristic space might cause a big change of their behavior. So we need to use this mapping strategy. And here is the detail about the mapping strategy. So overall, summarize we first randomly do a permutation of sub-problems, and then for each problem, we calculate the weight sum objective value of all individuals, and then we will map the individual with the best weight sum objective value to sub-problem. And the second method is to further enhance NSGP2 by propose 2 strategies, which is the semantic diversity strategy and the semantic similarity strategy. The semantic diversity strategy is to make sure all the generator of the rings perform differently to each other. And further, the proposed semantic similarity strategy also add a constraint between the distance of the parents and the offspring. In this case, we want to get a smooth convergence. And here represent the HV performance of all these methods. So actually, as we can see, MOGPD perform quite similar to SGP2, but SGP2 with diverse with semantic diversity strategy perform better than SGP2, and SGP2 with semantic similarity strategy perform even better than SGP2, and also perform better than SGP2 with the diversity strategy. Here is the IGD results, which is similar to the HB result. So that is mainly about the fundamental research of the genetic algorithm methods, and now it's about we bridge the gap between research and also the industry application. So for this part, we will talk about two real-world applications. The is workflow scheduling in cloud computing, and the second one is about inventory control. And for the inventory control, we consider two cases. The first one is to consider replenishment and transshipment decisions, and the second one is to consider replenishment and rental decisions. First, we talk about the workflow scheduling. Well, this application is mainly based on a guided robot project. This guided tour robot needs to complete a series of subtasks in order to fulfill the overall goal of a guided tour. And these subtasks have a certain order of execution and dependence relationship with each other. For example, it needs to perform human recognition first, and then might be do path planning, and then maybe manage speech output. So based on this requirement, we design a simulator like the figure at the right side. That is because for some tasks, it might take a long time to process if the device, obviously robot, to process itself. And sometimes for some tasks, the robot itself cannot process. And the robot may be only suitable for solving some very easy tasks. So the simulator can see that first, the device or the robot will release some workflows. The workflows represent a set of tasks for the guided tour goal based on a person process. And then we will use the routing rule to decide whether to allocate the task to edge or cloud, or just process the task by the robot itself. And also, once we decided the processing resource, we need to check whether the resource is idle. If they are idle, then the task will be processed directly. If not, it will be added to the waiting queue. This process is quite similar to the job shop scheduling process. So for the workflow scheduling, we still have routing rule and sequential rule, but different from the job shop scheduling. We need to design different terminals for these two rules based on the robot tour project system. And here represent the results of our proposed method and the normally used manual design methods. And we also do analysis about the terminal user frequency of the finally learned best scheduling heuristic. So as we can see that the processing time plays a quite important role in getting effective performance. And we also found for different scenarios or even different objectives, maybe the terminals used frequency are different. So this knowledge actually can further help researchers to propose new strategies to further improve the performance. And the second application is about the inventory control. The first case about the inventory control is the distributed material positioning. Manufacturing frequently occurs over multiple sites, but inventory planning for each site is often done in isolation of each other for the existing studies. But actually, we think coordinated inventory planning across multiple sites can further improve performance and reduce stock loss. And here is a example of this problem. We still have a lot of decision points, and at each decision points, we need to make two decisions. The first decision is the replenishment quantity, and the second decision is transshipment quantity between a pair of sites. And we test two approach. The first approach is a reinforcement learning approach that from a published paper. For the input data, you consider like inventory level or demand and demand forecasts and some others. And then we train a neural network by using the PPO methods. And finally, the actions for the actions, we provide a subset, we provide a set of selections, include the replenishment quality and the transshipment quality. But the limitation of this action space is that we need to do some tests at the beginning to get the general range of good performing selections. And we also test our genetic programming methods on this problem. For the genetic programming, we still have two trees, but different from job shop scheduling. The tree represents the replenishment policy and the transshipment policy, and also different from job shop scheduling. The rules are used to calculate the priority of machines and operations. And finally, the machine or operation with the highest priority will be selected. But here, our replenishment policy and the transshipment policy are used to directly calculate the quantity. And we test our genetic programming method and the reinforcement learning method, and also another very popular SS policy methods on the real-world data site. And as we can see that the genetic programming methods perform better on all the instances. And we also do the terminal frequency analysis. Actually, most studies have focused on analyzing the frequency of terminal use. However, it is also important to analyze the frequency of functions. So for this analysis, we also include this part. If we find that functions such as add and subtraction maybe occur more frequently, it may be because the policy should be a linear formula, and otherwise maybe it should be a non-linear formula. We also give the company proof of the strong interpretability of our GP methods. Here is an easy example. We simplify the rule learned, and then, for example, for this replenishment policy, this policy tends to order more stock when both the demand forecast and the safety stock are higher. So with the strong interpretability, user will have greater confidence in utilizing these policies. And the case 2 of the inventory control problem is to further consider partial information visibility. Multi-site inventory management presents a significant challenge, include demand uncertainty, and especially the limited inventory capacity, and maybe also high operational costs. And the companies, some Singapore companies must efficiently manage inventory across multiple locations, such as Singapore site and Malaysia site, where storage capacity may be insufficient. So one solution to this limitation is to renting inventory space from other companies. And the key objective is to maintain near optimal stock levels at each site while leveraging external rentals and to minimize the total cost. So here is an example. Still, we need to make the replenishment quality decision. And another thing is that we need to decide we need to decide the rental decision at other companies. So different from case 1, we add another parameter, which is the production capacity. And with this parameter, we can test how rental policy affect the total cost. And we provide some rental choice from other companies, and it includes 3 three types of information, like the price of rental and the quality of space of this rental, and also the rental months. And different from case one, that the total cost include the transshipment cost, lost sale cost, and order cost. The normal objective function include the lost sale cost, order cost, and also the rental cost. And here we consider the rental policy. Because the rental policy, similar to job shop scheduling, is also used to calculate the priority of a candidate rental choice. But differently, for job shop scheduling, we finally select only one, which is the highest priority one, as a final decision. But for the rental policy, after prioritize these candidate selections, we rental a set of additional space provided by different companies until the total requirements are sufficient. So that's about the application of genetic programming on some real-world applications. And now I will talk about the future work. Well, based on my experience on using genetic programming on the real-world applications, I find that not only on job shop scheduling, genetic programming actually can be used on a number of other problems like the workflow scheduling and also the inventory control, and especially inventory control. To the best of my knowledge, I find that the existing JP studies on inventory control is very limited. And also different from job shop scheduling. As I mentioned, the JP is to use to learn policies that directly calculate the quantities. So in this case, maybe we can propose some other strategies to improve its performance, because the search space actually is very big. And also we need to consider other real-world requirements. Currently, most studies focus more on time-related objectives like midspan, like flow time or tardiness. But in real-world applications, actually cost is very important. And another thing is that we already verified that the genetic programming methods can offer a better interpretability. But actually, for real-world use, if the learned policy by genetic programming is very complex, like it has a very dips, if the tree has a very large dips, and then its interpretability can also be not very good. So we still need some explanation mechanisms for explain the learned heuristics to users. And maybe we can consider human in the loop approach to improve the user confidence of users to using this learned policy. And another topic is about effective utilization of multiple scheduling heuristics. In my report, I already talked about a proposed method, which is to combine ensemble learning with genetic programming. And our methods is a work to maintain a population that include both individuals and ensembles. And that's to my best of knowledge, I think that's a first work for the dynamic flexible job shop scheduling problem. But I think some further strategies can still be proposed to improve the performance of these methods. And also we can consider many objective or multi-objective optimization with genetic programming. Currently, we find that SGP2 perform better than MOEAD, but indicator-based methods is not explored a lot. So we can consider this type of methods. And also maybe we can consider multi-indicator-based MOGP methods. And another thing is that currently transfer learning, feature selection, or ensemble learning has been integrated into JP for solving single objective job shop scheduling problem. But for multi-objective problem, we can still investigate this kind of integrations. And also maybe we can consider preference-based multi-objective optimization. And for all the methods mentioned in this report, you can follow this reference. Thank you for your attention.